Good evening, participants. Welcome back again to this first chapter of our 5 days training program on artificial remote sensing and GIS training on application of machine learning algorithm using remote sensing satellite images. Hope you are enjoying these sessions and also increasing your knowledge, which is imparted by our expert, Mr. Sabyasachi Kabiraj, sir. Before starting the session, I would again request you all to kindly ask your doubts in the chat section of YouTube Live, and do not forget to fill the attendance form at the last of the session, which will be shared through the chat box only. So with this, we can start our today's session. Over to you, sir.
Thank you, Subham. So let me know if you're able to see my screen. Yes, is it visible?
Yes. Yes, sir, it is visible.
So, yes, good evening to all. So, today is our third day, and according to the third day specification given over here, and we will try to learn this GIS data import to GE. This is not the import satellite data. This is a different kind of data import, as I already explained in previous class. So through asset to GE coordinator and then visualizations. And then we'll try to learn these basics of machine learning. So what are the machine learning algorithms are available in GE platform? Those things we will try to learn basics. Okay, so in depth, if you want to learn in depth, it will take more than 1 month or 2 months. So we won't go into the detail in this lecture. So we'll just try to see some of the basics, not through code, but through graphical user interface of Google Earth Engine. Okay. So here we can see the how human used to learn. So there are different kind of process of learning human. So basically we used to learn by memorizing the things through textbook or through something like some literature. So we are memorizing that, and through that we are learning. And the second one is through instruction given by someone, and then analogy, and then through examples. So these are the things, and at the last you can see observation and discovery. So these are the logic through which we are learning. Basically humans are learning by themselves. So after that, we can see here one example where mother giving instruction to her child and explaining about the behavior, how to behave, and those things. This is called explicitly, and the second one is implicitly. So this is by involving into the environment. This is outside. This involving the kid into the environment, and through this they are learning. So this is called implicitly learning, and this is explicitly learning. So in machine learning as well, we have different kind of learning methods. And out of that, you can see here, machine is learning through patterns from examples. And then it is able to generalize the new examples. So what is machine learning? It's about the programming computers to optimize a performance criteria using example data or past experience, right? So what generally machine is doing, we are giving some kinds of sample of a particular object, or we can say a particular pattern, and then machine is learning the pattern throughout the environment, we can say throughout the data we have given to them. And then based on the experience or example, or you can say inputs, it is predicting the other unknown things. Okay. So basically machine learning is two types, like supervised and unsupervised. In both the cases, learning is achieved by examples. So in the case of unsupervised learning, we only thing is we need to give a data input, right? And if you don't give label to the input data, that also fine, absolutely fine. And no explicit target output. So what does it do? This through unsupervised algorithm, it learns a probabilistic model to the input data. So using the input data, it is creating a probabilistic model, and through which we are not getting any label output. So it will generate depending on its own probabilistic model, the output. And finally, through that output, we are going to draw some inferences from the data sets. So what is the goal? So here the goal is to find the regularities and patterns in the input space. Here input space is in the satellite and beyond pure noise. So we don't want any noisy things. And the second is to find the clusters whose members are more or less similar, and understand the relationship between the variable by determining whether the particular observation falls into the different group or the same group. So depending on that, it will try to cluster. So cluster analysis, we can see divide data into meaningful group, that is called clusters. So objects within a groups are similar or related to one another, but it can be different also. So in that case, that particular cluster will go into the different category. But what is happening in this unsupervised learning? The unsupervised learning, we are giving some kinds of examples through which machine learning, and then that examples goes as an input, and then finally we are getting the output. So here, for example, band values of pixel in a satellite image are the inputs, and they separate the classes based on the input. For example, here the inputs we have given as a built-up region or non-built-up region, and then these two category will be predicted in the prediction output. Okay, so these two input we are giving to the satellite. Okay, these are the region we have built up and other regions are non-built up, and the prediction also will have the same category of output. And then here goal is use known output values, right? So we are giving a label. So for example, built up, non-built up, that is called labeling, and it is given by the user, or here we can say supervisor, to learn the pattern of the inputs. So here input is satellite image, and we are giving the examples, or we can say training inputs or data inputs, and it is labeled by the supervisor, or you can say the user. And finally, based on this input and the satellite image, it is predicting the output of new examples. So remaining region of the satellite image. So basically, the first step is collecting the training sample and assigning a label to that training sample. So here assigning labels to the training sample is basically, here in this example, two things. One is built up, another is non-built up. So these two things we are labeling here. And after that, we are giving satellite image different bands of satellite image. And finally, we are getting the prediction from the entire satellite image pixel. So each pixel, whether it belongs to built up or non-built up. So here we can see ground truth. That means whatever we are giving as input, that is ground reality. We know which is built up, which is non-built up region. So that is the input, and the output also be the same category. But in the new example, we don't have the output, so this only have to predict based on the band values. And here you can say built up and non-built up. And here we have input as a band values, right? But here we don't have the output. So that output going to predict through the machine learning. Now we'll focus on supervised learning, and what are the things are there in supervised learning. We will see one by one. So here I have given an example. Each instance in the data set is presented by some same set of features in n-dimensional feature space. Okay, so what is the ground truth? Ground truth is the training sets which we are taking, and that we are dividing into two different parts. One is training set, another is testing data. So we are taking the sample, that is called sample collections, and that entire sample collection we are dividing into two different categories. One is test and another is training, and those are labeled data in the case of supervised. And we use ground truth to learn set of rules, and these rules will be used by the classifier to generalize a new instances. So here we can see the feature 1, feature 2, feature 3. So n number of features are there. And then similarly here also we have n number of feature. And finally we are leveling here. So here whether the feature is built up or non-built up. So likewise. So generally this process of supervised learning is starting from what do we want to classify. So first you should have a clear understanding what you want to classify, whether we are classifying the built up, non-built up, or whether you are classifying vegetation area or non-vegetation area, like that we want to classify. And it depends on the objective, research objective. So it can be anything, right? So it can be any object as well, water body area or non-water body area, like that also we can classify. It depends on the purpose. And then which data set do we need? So this also we should have a clear understanding for this particular thing. Okay. So if your aim is to classify the built up and non-built up area, or to differentiate built up and non-built up area, so what are the band you need for that? So those things you should have a clarity before jumping into the classification process. And which attribute or features will we use? So these are the three things is very important. And remove noise. Identify and remove as many irrelevant and redundant features as possible. Construct new feature from the existing features. And select instances for the training samples. And select algorithm here. Select the learning algorithm. So this is also very important, which algorithm you want to run. That is also very important. And after that you have to run the algorithm, and then the process to evaluate the algorithm on test or validation data sets. So first of all you will get the output, and then that output we need to validate or test the accuracy, called validation accuracy or test accuracy. And this validation accuracy or test accuracy can be measured by different kind of methodologies. You can see here cross validation, leave one, leave out, then k-fold cross validations. So those are the different kind of methodology through which we can do it. We can find out the test accuracy or validation accuracy. And this tune parameters is the last one. Is different features, a larger training sets, or too many dimensions. So these are the questions we'll have in our mind. So how to overcome from this? And to overcome from this problem, we have a tuning the parameter, tune the parameter. Okay. So this is also very important. One of the important parameter in machine learning, that is called hyper tuning. So coming to the graph, if you see, we have a problem, and that problem is related to this, what we want to classify. So that particular thing is a problem. Now, based on the problem, please try to find out the data related to the problem. So what are the data is related to this problem? So those things you have to find out. And then after that, we need to go to the data pre-processing technique. So we need to remove the noisy pixel or cloudy pixel. Those things we need to remove it. And finally, we need to generate a clear image where we can see all the features clearly, right? And then we'll introduce a training data sets. And these training data sets will put together into the algorithm, and this algorithm can be supervised, any supervised algorithm. And this is training data set which will come to the training algorithm in the algorithm of machine learning, and then this data also will come into this. So we'll have a training data, and at the same time we have to run the training data set based on this data, which after pre-processing this data will come over here, and after this training we'll get certain output from the training data set itself. So the prediction will come under the using the training data sets. So here the training data sets will be there, and then this data pre-processing, all bands will be there. And based on these two things, it will predict the output, whether the region belongs to built up or non-built up. And after getting those classified image, built up and non-built up image, that classified image, this will go for the evaluation process, further evaluation process. How you will evaluate? So we already separated the training sets and testing sets of data, and that testing sets of data will use for the validation accuracy. This particular output will be used for this validation accuracy to get the validation accuracy. So here, what are the things will get involved? First of all, the classified image which you are getting from the training data sets, and then the second one is testing data sets. So this testing data sets will go and we'll see whether the particular whichever we have taken from the training samples, or we can say the sample collected samples. So we already have ground truth samples. So those samples will be divided into training and testing, and that testing part will take over here, and finally we'll try to see whether the classified image and what is the accuracy of that particular image. That is finally the validation accuracy. And after that, if the validated image, or you can say classified image, is correct, then we can take it. Otherwise, if it is not classified properly, it will again go to the hyper tuning process. So here we need to tune the parameter again, and then again the model will run, again it will generate the output, and likewise this cyclic process will happen. So this is called machine learning. Till you are getting the proper output or the user satisfactions, it will run continuously. So user has to confirm that whether the output is proper or not. If it is not proper, again you need to go to the hyper tuning, again you need to fix your parameters, and then run the model, and then try to validate the model and see the validation accuracy is correct or not, and then the final output will generate, right? So these are the process involved in machine learning. So here you can see the cross validation methods. So what are the methods are there in cross validations? So this is actually cross validation in the sense of validation accuracy, right? Validation accuracy or testing accuracy. Testing accuracy. So the one of the method is holdout method. So in this method, what it is happening, the data is set and is separated into two sets. One is training and the testing. So you have collected the training samples. So for example, your training samples around, or you can say you have collected the sample and your sample is around 200. Now this 200 number of sample, you are dividing into two sets. One is training and the testing. Now you have to consider the percentage of division. So for example, 70-30. So if you are making 70% of the sample as a training sample and remaining 30% sample as a testing sample, right? So that way this 200 sample will get divided into this two training and testing samples, right? And the evaluation can have a high variance, depends on the random samples. So it can have a higher variance, no issues. Okay. And then the second method is k-fold cross validation. So what is this? The data set is divided into k subset. So you have a data set. So for example, I have divided the entire data set into 4 zones. And then this k subset means this 4, k means there is a number. It can be 4, it can be 5. It depends on the number of sample you have collected. So here you have collected 200. So you can go by 5k. So 5k or 5 cross validation. So 5-fold cross validation. Here the k means number, right? So what it will do, it will divide your entire data into 4 or 5, whatever you will define. So let's assume k number of subset, and the holdout method is separated by k times. So what it will do, out of this 4 or 5 subset, it will consider one subset as a testing subset, and remaining 3 will be used for training subset. So this process will run for 4 times. And finally, for each time you will get training and testing accuracy. And by putting the average of all the 4 times training and testing accuracy, final accuracy will get it. So this is a proper method to do cross validation. So many researchers are using this is the as a standard version. This k-fold cross validation, many researchers are using as a standard version, and scientists are actually trying to use this k-fold cross validation, because this will have a proper explanation in each subset of data. Leave one out cross validation. Now here, these two more or less same, just in the case of k-fold, here k equal to n. That's the difference. N means number of sample. The last one is repeated k-fold cross validation. So here it is not repeated. Maybe this is one time process, but here the process will take 4 or 5 times. So that process is same only, but it will run for one time, and this will run for multiple times. So that's the difference. And it will reshuffle before each round. So each time you will get different set of training and testing samples. So for example, particular this subset, if first time goes for testing, the next time this will not get selected for testing sample. Next time this particular subset will go for testing sample, and remaining this 2 and 3 will go for training. So each time model will get different subset of training and testing data, and then model will evaluate the final validation accuracy. So this will be a very standard, I can say very standard version of cross validation method. Then coming to the detail for k-fold cross validation, you can see here the standard 5-fold cross validation. So here you can see the k they have taken as a 5, right? So you can see 1, 2, 3, 4, 5, and this side also 1, 2, 3, 4, 5. Now this particular block, if you see, is taken for test, and the remaining all 4 block is taken for training data set. Sorry, this training. And after that, if you see, this particular block, or you can say subset of training data, subset of data set, is taken for testing purpose, and the remaining other, if you see this one, and this one, they have taken for training. So you can see each time the testing data set is changing, and similarly the training subset also changing, right? And now finally you will get an accuracy of all this, and you will calculate the accuracy rate, right? Example you can see here. So here you can see we have given orange over here. This is not roten one. So detecting roten oranges from photos. So these are the photos we have, and we began with a set of 600 orange labeled as positive example and negative example. So if it is roten, we will tell positive, and if it is not roten, it is a negative, right? So these are the three samples, for example. And then learn the characteristics of the classes. Find the description shared by all positive examples. So positive example in the sense roten one, and all negative example is non-roten. Okay. So according to the expert, the feature that separate roten from non-roten oranges are based on size and based on color. So these are the two parameters they have identified, right? And these features are the inputs for class recognizer. Now in this case, this is color and size, but in remote sensing, it may be different kind of band or indices or whatever it is. So you have to first select the parameters. Based on what? Based on the prediction, what you want to predict. So the based on the predictor only, you have to select the parameter. So you are trying to predict built up, but if you are taking the parameter of detection of water bodies, so that particular algorithm actually wrong. So the selection of parameter is very important in machine learning. So here in this case, you can see the size and color is only the determinant factor for this orange, whether it is positive or negative, whether it is roten or non-roten, right? So these features are the inputs for the class recognizer. And we will predict the response value, or we can say output, by these points, right? So these two are the predictors, or we can say parameters. Now, in the case of training samples, so take 400 oranges, and out of 600, so total we have 600, out of 600 we have taken 400 as a training data sets. So remaining 200 we have as a testing data sets, right? So these 400 oranges will train the model how to determine whether an orange is roten or non-roten. Based on what? Based on two features, size and color. And then finally you will get a prediction, right? Or we can say prediction or output, whether the particular orange is roten or non-roten. Now you will get the prediction. Now this prediction will, using this predicted output, you can say, will try to find out the validation accuracy using this 200 orange. So this 200 orange will put it over here and overlap with this roten and non-roten oranges. And if our 200 oranges are like roten and non-roten, both things will be there in this 200 orange as well. So we'll try to check the accuracy with this as well. So first we'll get the training accuracy from this itself. Now for testing accuracy or validation accuracy, we will have a separate testing data sets, and based on these oranges, we'll try to test this predicted output, right? We try to test it, and finally here we'll get the validation accuracy. So for each instance, predict whether the orange is rotten or not. So examine the accuracy of the classifier, evaluate how many oranges were classified correctly. So out of these 200 oranges, how many oranges is correctly classified? So that will determine our accuracy, or you can say validation accuracy, right? So often we will divide the data into three groups. One is training, and then test and evaluation set. Is to evaluate the performance of the mode, but generally most of the cases we only divide these two, because we need some training sets to train the model, and it will give the prediction or predicted output, and this predicted output we need to test it using the testing sample. So these are some of the machine learning techniques in Google Earth Engine. Okay, so first one is decision tree, the second one is cart classification and regression tree, the third one is random forest, and the fourth one is support vector machine. We'll start with decision tree. So we can see here the instances are sorted based on feature values, right? And each node, so these are node, you can see these are node. Each node represent a feature to be classified. Each branch, so this green is node, actually, okay, sorry for this. This is node is represented in green. So you can see these are the node, and branch is represented in red. So these are the branch, and then root node, which is given over here. So this is the root, and finally these are the different prediction. So each branch represent a value that the node assumes. Classification begins at the root node, so it will begins from here, and instances and sorted based on their feature values. The optimal decision tree is one with a minimum number of branches and intermediate nodes, a higher predictive power. So this way the decision tree will work, and finally based on the voting methodology it will predict whether it is yes or no. So you can see the data structure will come something like this, and our model will look something like this. For example, where if you see this data set, so through this data set we want to predict whether we want to purchase the computer, yes or no, right? So this is the age group, and this is the income, then student, then credit rating, and buys computer. Okay, for example, you can see here we have a student. If the student is yes, and then we will check again with the income. Here also, if it is yes, again it will check with the another filter called income. And if the income is high, then it will ask for the age. If the income is medium, then it will ask for credit rating. And then again it will have a two different kind of things. So likewise it will reach, and finally you will get this kind of things. So here you are getting no, here you are getting yes, you are getting yes, here you are getting no. So likewise you will get the final result like this. And finally based on the voting performance, so what is the majority saying, that only will be the final decision. Okay, then coming to the next one, classification and regression tree. So here this is also kind of decision tree, but it is only having two options, yes or no. So is age less than 25, is ethnicity Jewish, So likewise, it will ask yes or no. There is no other option. So cart will consider all the data and search for all possible variable, all possible values in order to find the best split. So nodes are continuously divided into further nodes: root node, children, and then grandchildren, and then finally terminal. And the goal is to maximize the difference between the proportion of entities that pass to each new nodes, and thus splitting variable based on the exhaustive search of all possibilities. And the advantage is it can deal with complex combination of dimensions. For example, if you are this built up areas will have always have B1 that is larger than B2, but only B3 is lower than B1. In that case, B2 is larger than B1 and may cause overfitting with the training data. So there is two kind of error in the machine learning. One is overfit and underfit. So those are the two things we'll discuss later stage. So the thing is, next one is random forest. So here each tree depends on the values of random vectors that are sampled independently with the same distribution per tree. The randomness is either in the selection of samples in the training or in the selection of random sets of weight. So after key trees are generated, it votes for the most popular class. So here the majority vote or mean. There are multiple methodology. So you have to select the methodology, whether you want to go with the majority vote or mean or something like that. So the advantage is it's very useful in remote sensing. So in the case of large databases and computational needs. So whenever you have large database and computational needs, you can go with random forest model. So it will it is again another advantage is reduction of training data set size and noise generally do not have a significant effect on the classifier accuracy. Coming to the support vector machine, and this is actually a different kind of things. You can see a relatively simple but supervised machine learning technique where we are always try to find out the maximum margin to separate two different classes. So what is happening? It is trying to maximizing the margin between two classes. So largest possible distance you can see in the diagram, or you can say in the figure. So this is the two classes. You can see the one is in white color, another is red color. So it is trying to maximize the distance between these two classes, and the vectors, or you can say the samples, which helps to find out the distance between two different classes is called support vectors. And maximum margin decision hyperplane, so these are called margin. You can see, so this entire distance is called margin is maximized. So these are the margin. This was one margin and this is one margin, and this is the maximum distance. So it is saying the maximum margin is maximized. Okay, so likewise it will create a maximum distance between these two classes to classify the different categories. So here one and then here one. So here you can see the support vectors are used to define the position. So this support vector, this is one support vector, and this is one, and this 2, 3. So this 4 support vector is defining the position of the best separating hyperplane, right? So this is the hyperplane. You can see in between this. This is the hyperplane. The distance from the decision surface to the closest distance data point determine the margin of the classifier. So let's have a look or example. So we'll look through GE Explorer, and we are not going with the code editor. Okay. So first, what is the steps? What are the steps we need to follow for this? So first we need to define the classes. So whether it is built up or non-built up. and then construct a training sets either by drawing polygonal points or by calling a level feature collection. So if you have your existing training sample, you can import it. Otherwise, you can do by drawing it. And then call the image you will use for the classification. So this will go as an input, or you can say parameters. And then specify the resolution of the pixel created during the training process, and choose the classifier and then perform the classification, right? So these are the 6 steps you need to follow to run a classifier. And what are the classifiers are there? You can see here, it is listed over here. So we have a this one and this one, and we have a lot of classifier. You can see all are machine learning classifier. So how you will do that? So I hope all of you have Earth Engine Explorer access. If you don't have, please try to log in or sign up first of all into the Earth Engine, and then you will have a access to the Explorer. So in Explorer, what we need to do? First, we need to go to the add data option, and then through this add data portion, we need to go in this vectors where there is an option called hand drawn points and polygon. Okay. And then if you have already a data with you, you can upload also. Okay. The second option is, now once you have digitized, so you can see here is untitled class 1, untitled class 2. So now you have to give a title to this class. So here is an option called add class, and in that we are renaming it as a built up and non-built up region. And then next is click on add data. So here is the option called add data, where you need to choose your satellite image which you are going to use for your classifier. So this satellite image bands will be your parameters for the prediction. And then you need to select the year. So you need to select the latest year or whatever it is, and then save it. And after that, you can see here, we can select another parameter if you want. So for example, here I have selected NDVI of Landsat 7 annual composite. So you can select that also if you want another predictors. So likewise, you can take Landsat temperature as well, LST data also. You can create other data as well, so that as a predictor. Okay. So here we have predictor as a NDVI. So here you can see the Landsat NDVI composite, this one. And then we have a different bands. So likewise, we need to fix the number of parameter. Now here you can see we are adding the bands through this add band option. And finally, you can see we have 7 bands over here. You can see 7, and then 1 annual NDVI is 1. So total 8 parameter. And after that, just click on save and apply. And then we need to train a classifier. How you will train? So first of all, set the new layer as input layer, and set the input of the 2 other images don't use. So these are the things you have to set it first. Okay, so like this, you need to select. You can see here as an input, and then another is don't use. So those options are available. And then click on built up and draw the sample on built up areas. So now your collection of samples will take place. So from here, you need to take the polygon, and you need to draw the polygon here and there. You have to draw the polygon. So here you can see, so here the built up areas showed in red. So these are the samples. and then non-built up area, these are the green polygons are the non-built up area. And then we need to choose a classifier. So what classifier you want to select for the particular model. So here we have all the models you can see listed over here already. I have shown in the previous slide. And here in this case, we have selected the CART classification and regression tree. And then we need to fix the resolution. It is here 30 meter. And finally, we have trained the model. You can see here we have trained the model. We have clicked here to train the model. And finally, we are getting this kind of output, right? So here the red area is representing the built up region. You can see this is red, is shown in red, and non-built up is as a green, right? And then we can get an accuracy, training accuracy, or overall validation accuracy, both we will get one by one. So how you will get the accuracy? So you can see there is a built up and there is a non-built up. Okay. So for example, your total number of sample is something around 3,528, and out of this 3,528, how many polygons or samples correctly classified? So for example, out of this many samples has been correctly classified, and this TP is denotes true positive. This is false negative. This is positive, this is negative, false positive, true negative. So if a classifier correctly classified the image, the original, based on this only the accuracy will come. It depends on this. So out of 3,528, 3,230 samples has been correctly classified, and the remaining this 298 samples is misclassified. Okay. Similarly, non-built up area, the total number of sample you can see here 5728, and out of that 162 sample is misclassified. So misclassified in the case, it is classified as a built up, and this is as a non-built up. And finally, we need to calculate the percentage. So if you consider this as 100, so what will be the percentage of this? Similarly, if you consider the total percentage like that, you need to calculate. And finally, you can download the model output as a TIFF. So you can see here, there is an option called download, and you can download here. Thank you.
Thank you very much, sir. Sir, I can see questions from participants. The first question is, in which method we pre-process the data? Can you please explain?
Pre-processing in the sense of the removing of cloudy pixels. It can be, in my previous class, I have explained to make the satellite image in a median. So if you keep in a median statistic, for example, you have a date range, starting date and ending date of the satellite image, and in that entire date range you are getting, for example, 30 or 40 satellite images. So if you keep it as a median, so what it will do, it will remove the darkest pixel as well as brightest pixel. So it will at least remove your noisy pixels. Okay, so that is one kind of pre-processing. The second is removing the cloudy pixel by filtering the cloud percentage. So that is the second one. Okay, so these are the two pre-processing technique generally researchers or scientists are using. Okay,
Thank you very much.
Yeah,
Carry on, sir, please.
Yeah, these are the two. You can go ahead to the next question.
Okay. So the next question is, could you please suggest some good source material or online material for learning machine learning in context of special sciences?
Yeah, this is kind of, we are also conducting GeoVigyan, conducting the machine learning things online. I think it will be in December, so you can join that class as well. And besides that, you can refer a lot of online resources available. And if you search simply in Google, you will get a lot of research. Besides of that, along with that, you can do searching in Google Earth Engine platform itself. They have a lot of documentation part. You can go through that. Once you go through that, you will have a basic understanding at least how to write a code or how to run a program. See, here I have already only shown the basics. It's not in-depth programming or in-depth machine learning. In in-depth machine learning, we'll have a hyper tuning process, and those processes are not available in GUI, graphical user interface, which we have shown in this. And those hyperplane or hyperparameter tuning, you can say hyperparameter tuning, that particular thing will come in code only. So you have to write a code, and then we have to find out the accuracy, and based on accuracy, again we have to train the model. Likewise, it will continuously cyclic way, the model continuously will run till the users get satisfied. Okay, so you can follow the Earth Engine documentation part.
Okay, thank you very much, sir. The next question is, what are the minimum and maximum samples to be taken for training samples, and which is best, either to take training samples as point or polygons?
See, it depends on the objective or what you are going to trying to classify. For example, if you are trying to classify built up, in this case, you can take as a polygon, because built up is having a huge area. So always try to remember, while you're taking the training sample, inside that training sample, there should not be any misclassified pixel. So what I'm trying to say is, for example, you are drawing a polygon for built up, right? So in between the pixel, you will have some vegetation coverage or soil or bare soil. That kind of mistake should not be there. If you are not doing that mistake, if your pixels are pure, that's strong enough to run a model. Okay.
Okay, thank you very much, sir. Sir, there is a request from a participants. If you could please provide some Google Earth Engine code, a small one only, just like a hands-on session with that.
Yeah, we'll do that. I think we have a hands-on session on, I think, next or I think last day. So definitely I will show you at least one class. I will teach you, definitely.
Yes, sir. Moving to next question. Can you please suggest any book for this machine learning or Google Earth related?
Yeah, there are a lot of documents available, and it is already published using Python. And also it is there in the Earth Engine documentation part. You can refer that. It's a well documented things in Earth Engine portal itself. So go there and search each and everything. If you are facing any kind of error, search in Google and you will get the possible solution for that particular error. Okay. Even you are not getting there also proper solution, you can reach me out. I will try to help you out. Okay.
Okay. So the next question is how to decide a specific algorithm of machine learning according to data sets.
See, it's again depends on the objective, or it again depends on the area of interest, region of interest. So there are a lot of things you need to consider. So I will give you an example. For example, if you are trying to classify object based classification, so in that case you need to consider the shape of the object, shape, size. Like we have mentioned in our PPT that there is a shape of orange and then color. So in that case, these two things is very common in all the objective. For example, in forest cover, new tree plantation, if you are trying to classify new tree plantation, so there will be a round shape because the soils has been deposited on the root region, so there will be round shape. And the size, and how many pixels are there. So those kind of things, first of all, we need to find out. So what is the exact size and shape? And the second one is what is the reflectance. So these are the parameter, first of all, you need to find out. And then we have to think what classifier we should run. Okay. So if you are not sure which particular classifier we need to use for our study, always go with the better classification process. For example, algorithm. For example, random forest is the one of the popular machine learning algorithm that will give you a perfect output. But I can't say always random forest will give you a perfect output. And besides that, support vector machine also sometimes gives better output than random forest. So I will suggest you can opt in these two methods. You can run random forest and you can do support vector machine as well. And if you're trying to find, like, publish or write some research article, you can do a comparative research between these two algorithms. So which particular algorithm is giving better accuracy. Okay, so there are a lot of such article available on internet online. Just do searching, you will get the output. Yeah.
Okay, so moving to next question, is Earth Explorer different from Earth Engine? And you had made mention if we have Earth Explorer access, kindly clarify.
See, whoever registering or whoever signing up in Google Earth Engine, they will have access to the Earth Explorer. It is open to all. It is not only to me, it is open to all. Just search in Google Earth Explorer, Earth Engine Explorer, not Earth Explorer, Earth Engine Explorer, and it will lead to you to that particular website, and just explore it accordingly. I have mentioned in the class, you will get all the things.
Okay, sir, I think this question is repeated. Does the choice of machine learning algorithm depend on data set or type of analysis to be done?
Correct. It depends on the parameter, it depends on the sample, or depends on the objective which we are trying to predict. Okay, so there are all the things we have to consider. And finally, see, even no one can answer this particular question, which particular algorithm we should use, because if you see, a lot of researchers are going on continuously, and they are only looking which particular algorithm is perfect for the particular object. Okay, so in some cases we have seen that random forest model is perfect for this particular job, and then in some cases we have seen support vector machine is best when they have compared all the machine learning. So it is like it will always change, keeps on changing. It depends on the objective. Okay, we can't say that this particular model we should always use, or this one you can use always. You can't say that. We have to compare.
Okay, sir. Thank you very much, sir. I think there. Can you help? Okay, sir. I think this we can do later. Thank you very much, sir. I think we are done with today's questions, answers, and thank you very much again, sir. So, participants, we will meet tomorrow again at the same time, and please do not forget to fill the attendance form which is circulated through the chat box of YouTube, and we will meet tomorrow at same time. Thank you very much.
Thank you, Subham.